Let's talk more about a vector's magnitude. If we know a vector's components, we can always calculate a vector's magnitude, which, as we know, is the vector's length. We can explain how to do so with a two-dimensional example. I have a vector v with x component 3 and y component 4. Now, all vectors form a right triangle. If you squint hard enough, you can see it. In fact, I've drawn the triangle here. This triangle is formed by the vector v. Now, when it comes to a right triangle, we call these two sides legs and this side the hypotenuse. It's always the side that's opposite the right angle. Now, we can always calculate the length of one of the sides of a right triangle if we know the lengths of the other two sides. They're related to each other with this theorem right here. We call this the Pythagorean theorem. It says that if we call the hypotenuse c and the two legs a and b respectively, that c squared equals a squared plus b squared. Now c is the length that we're after here. This is what we want to figure out. We already know a and b. A and b are simply the x and y components of the vector. In this case, 3 and 4. So how do we solve this equation for c? Well, we take the square root of both sides of the equation in order to get c by itself. So the square root of c squared is simply c. And the square root of the right side, well, that's the square root of a squared plus b squared. We have to take that whole quantity and take its square root. Now, in mathematics, the answer to this equation is actually plus or minus the square root of a squared plus b squared, because either plus or minus this value, when you square it, gives you c squared. But when we're talking about lengths and distances, we don't care about a negative because we can't have a negative length. So really, the positive answer is the only answer we care about when calculating the magnitude of a vector. So using this formula, which is derived from the Pythagorean theorem, we can calculate the length of vector v for this vector. We know x, we know y, we just want that hypotenuse of the right triangle formed by vector v. Now, if we have a vector v, we can place v inside of two vertical lines, and this denotes magnitude. So this says the magnitude of vector v equals, and we need to calculate the length of the vector using our formula derived from the Pythagorean theorem. That's going to be the square root of a squared, which is 3, so 3 squared, plus b squared, which is 4, so 4 squared. And this simplifies to the square root of 9 plus 16, which equals the square root of 25. And the square root of 25 is simply 5. So the magnitude of vector v, in this case, is 5. Now, this formula for the magnitude of a vector, derived from the Pythagorean theorem, actually works in 3 dimensions. Now, I have a 3-dimensional coordinate system with x, y, and z axes, respectively. Now, let's say I have some vector, a 3-dimensional vector, and I start it at the origin, and I draw this vector like so, and we'll call this vector v. Now, v has x, y, and z components. Now, we'd like to calculate the magnitude of v. And we know that all vectors form a right triangle, if you can find that right triangle. Now, in order to prove to you that the Pythagorean theorem in 3 dimensions works, I'm going to reduce this to a 2-dimensional problem first. So the vector v, I'm going to take its tip and draw a line straight down in the z direction. And I'm going to draw a vector from the origin to that point. Now, this vector is the same as vector v if we were to take its z component and zero it out. We'll set that z to 0. And now we have this vector, which if we only consider the x and y, we now have a 2-dimensional problem. Now, if I draw the y-axis, and I draw the x-axis, and I draw this vector, this now 2-dimensional vector, I can draw a dotted line down to the x-axis, which in 3 dimensions would be this line here. Now, I know the x direction is pointed to the right and the y direction is pointed up. So really, this is what we're looking at if we're looking up towards the z direction from underneath, but that's okay. This is now a 2-dimensional problem, and the right angle is right here. So this vector that we've reduced down to 2 dimensions, we can call vxy because it only exists in the xy plane. So vxy has x and y coordinates, and these are the same as the x and y coordinates of the 3-dimensional vector v. And we know how to calculate the magnitude of a 2-dimensional vector. We simply take the square root of x squared plus y squared. This gives us the magnitude of this 2-dimensional flat vector. But we really want the magnitude of v, our 3-dimensional vector. So how do we get that? Well, if we look at our 3-dimensional diagram, v forms a right triangle with v sub xy, that 2-dimensional flat vector, where the right angle is right here. So we could represent this problem as another 2-dimensional problem. We have v, and we have v sub xy, and we have this dotted line going straight up to the tip of vector v. Looks like I didn't quite draw it long enough, so there it is. And this is the right angle here. We see that right here. So once again, we can reduce this to a 2-dimensional problem, and now we can solve for vector v. We know the length of the dotted line here, it's simply z. And we know the length of this vector, it's v sub xy. It's the square root of x squared plus y squared. So let's calculate the magnitude of vector v with the quantities that we know. Vector v, magnitude, is equal to the square root of this length squared plus this length squared. We know this length, v sub xy, it's the square root of x squared plus y squared. So that's the length. We're going to square that. And we know this length, it's simply z. So we have z squared. And the square root of x squared plus y squared squared is simply x squared plus y squared. So this simplifies to x squared plus y squared plus z squared. That is the magnitude of vector v. So essentially what we have is a formula for calculating the magnitude of a 3-dimensional vector derived by using the Pythagorean theorem 2 separate times. One for this right triangle, formed by zeroing out the z component of our vector, and one from this right triangle, formed from that flat vector in the xy plane and the vector in question, vector v. So now we know how to calculate the magnitude of any vector, whether it's 2-dimensional or 3-dimensional. And this can come in handy in a number of scenarios. Let's just really quickly talk about one of those scenarios so we get an example. Let's go back to 2 dimensions. I'm going to draw a y-axis and an x-axis. Now let's say that we have 2 points in space. We have a point right here, and we have a point right here. We'll call these points 1 and 2. And these points have 2-dimensional coordinates, and these can be represented by vectors starting at the origin and ending at those points. So here we have the point represented by the vector v1. And here we have the point represented by the vector v2. We can say that v1 represents the location of a character and v2 represents the location of an enemy. Now let's say we need to know the distance between these 2 objects. We want to know how far apart they are. Well, we can represent this by a vector from v1 to v2. And we know how to calculate a vector using 2 points in space. We simply subtract x and y coordinates. We know that v sub 1 can be represented by x and y coordinates for point 1. We'll call these x1 and y1. And v sub 2 can be represented by the x and y coordinates of point 2. We'll call these x2 and y2. And we can calculate the vector from point 1 to 2, v sub 1 to 2. And we know how to do that. V sub 1 to 2 is simply x2 minus x1 and y2 minus y1. This is review. We already know how to do this. Now, we want to know the distance from v1 to v2. That's simply the magnitude of v sub 1 to 2. So if we want the magnitude of this vector, we know how to do so. We have a formula, right? Well, let's call this vector from 1 to 2 vector 3. And vector 3 has x and y components, x sub 3, y sub 3. And those are calculated here. Well, let's calculate that vector magnitude. V sub 3's magnitude is the square root of x sub 3 squared plus y sub 3 squared. This gives us the magnitude of v sub 3, which is the vector from 1 to 2, and that magnitude is the distance from v1 to v2. So a vector's magnitude is really a distance formula. We can always find the distance from point 1 to point 2 by taking the vector from 1 to 2 and calculating its magnitude. Great job. I'll see you soon.